This is actually not a bad time to talk about the Banach-Tarski Theorem, a theorem that students in mathematics should see. This is a bit of an eye-opener the first time you see it, but that's probably good if you have your eyes opened. Here we start with a closed unit ball in Euclidean 3 space. The theorem says that we can dissect or partition the ball into 5 parts, which can be rigidly moved to form 2 new unit balls. By rigidly moving, we mean allowing rotation and shifting operations, but without any distortion. No stretching, no compressing or anything. All the distance is being preserved. And of course, there should be no gaps or overlap between the 5 pieces once we reassemble them on the other side. That's what we mean by partition. The original theorem gave this result, but with an unspecified finite number of pieces. Nowadays, we know that you can do this with 5 pieces, but actually not fewer than 5. This theorem does use the axiom of choice, like so much of the stuff we do. And as I mentioned in a previous video, it's customary to make that point clear as a kind of disclaimer. Here is my animation, which is intended to visually suggest the statement of my theorem. You shouldn't take any of these pictures too seriously. They're purely figurative representations of the kind of rigid motions involved. And in fact, the 5 pieces in reality would be extremely intricate in shape. So this animation here you should take with a bucket load of salt. The actual 5 pieces are so convoluted that no visual image can really do them justice. The theorem is referred to as the Banach-Tarski paradox by a lot of people. They call it a paradox because of its counterintuitive nature. But it's not a paradox in the same logical sense as Russell's paradox, which pointed to an inconsistency in mathematics itself. Really, the only inconsistency in the Banach-Tarski result is between the mathematical reality and the interpretation in some people's minds. Certainly, the theorem is not saying that we can take a solid ball of something like gold and cut it up to form 2 new balls the same size as the original. We cannot do that with matter because of the intricacy of these shapes, which would require splitting atoms, even splitting elementary particles, to make this operation work. Ultimately, the construction fails to apply to physical objects because it would violate conservation of mass and conservation of volume, for that matter. But of course, the puzzle of the Banach-Tarski theorem goes much deeper than physical objects, because without even concerning ourselves with the physical structure of matter in a ball of gold, atomic structure of matter, we could ask about physical space itself. Doesn't this exercise violate conservation of volume? If you imagine a unit ball of empty space, even without any matter to occupy it, doesn't the Banach-Tarski theorem say you can double the volume of any region of space just by performing these rigid motions? It turns out it doesn't. Because the universe is not R3, our ball is not region of physical space, whether solid or empty. It goes back to what I said in the earliest video, that the real numbers are one conceptual number system with maybe surprisingly useful applications, but let's not push the metaphor too far. We start giving real number coordinates to space, and it's a reasonably good approximation to reality until we exceed the limits of that particular description. And the Banach-Tarski theorem does that. It goes way beyond the limits of what the model is designed for. There are many other examples of apparent paradoxes that simply point out the flaws of our thinking of physical reality. And by the way, they don't all rely on the axiom of choice. You should already have smelled a rat when I started talking about a closed unit ball. What is a closed unit ball? In the physical world, is that anything different from an open unit ball, let's say of gold? The difference is an important one for us in doing mathematics, but in the physical world, there's no way to talk about a closed versus an open unit ball. The fineness of that distinction makes sense in mathematics, but not in physical reality. And if you can't distinguish open from closed in physics, you certainly can't interpret this mathematical dissection as a dissection of physical objects, even physical space. Now, there are many people who would answer this puzzle differently from the way I'm doing it by starting off by saying, oh, the problem is the axiom of choice. That always leads us to counterintuitive results. And I refute that answer on several levels. For one thing, there are many theorems in ZF mathematics which achieve equally preposterous-sounding conclusions without using the axiom of choice. For example, the fact that there's a bijection between R3, the set of all points in real 3 space, and the set of points on a single tiny interval of the real line. That bijection does not require the axiom of choice at all, and it can be given by a very explicit formula. Evidently, the real number description of physical reality is a model whose limitations we have simply exceeded in this way. Coming back to the mathematical world, is there still any inconsistency even in the ideal mathematical setting? Does our Banach-Tarski operation violate the conservation of volume even as defined in the conceptual mathematical sense? Actually, no. Because how do we define volume in the mathematical setting? We start by defining volume of a box, its length times width times height. And from there, you try to define volumes of other geometric solids by using upper and lower Riemann sums. We look for better and better approximations using Riemann sums with finer and finer partitions. You hope that upper and lower sums eventually converge to the same limit, and when they do, you have a well-defined answer for the volume of the region. Now, there are improvements on the Riemann integral for talking about volume of different three-dimensional objects. But our 5 pieces are so convoluted that it is impossible to have any meaningful value for their volume, whether you're doing Riemann integrals or Lebesgue integrals or whatever. The upper and lower Riemann sums are just too far apart. They don't converge to the same value. No well-defined value for the pieces means there is no true paradox. The illusion is created by our mistake in thinking that the real coordinate description of physical space is a perfect fit. As far as the axiom of choice goes, you can use it or not according to your personal preference for doing mathematics, but you can never deduce an inconsistency from the axiom of choice unless there was already an inconsistency without it. But if you thought that Banach-Tarski theorem was bizarre, this is where I think it gets really more strange. There is a similar statement in any number of dimensions, particularly higher dimension 4, 5, 6, and there the Banach-Tarski theorem holds as well in higher dimensions. But in 2 dimensions, the analog of Banach-Tarski does not hold. In other words, there is no way to dissect a closed disk in R2 into any finite number of pieces, and then reassemble them using rigid motions to form 2 closed disks the same size as the original, with or without the axiom of choice. It's just impossible. We can certainly dissect a disk in strange ways, get pieces with no well-defined area. There's no way to reassemble them, however, to form 2 disks. Obviously, I'm talking about the conceptual picture here. So the obstruction is certainly different than what we saw in 3 dimensions. If you want a counterintuitive result, I find that this result is more counterintuitive than Banach-Tarski. That's my personal sense. And by the way, in 1 dimension, once again, it is impossible to dissect or partition a closed unit interval into finitely many pieces and reassemble them to form 2 closed unit intervals. At this point, I should mention that for proving the results on this slide, the essential tools come from analysis, generally, or more specifically from measure theory. For the proof of the Banach-Tarski theorem itself from the previous slides, the essential tools are not really analytic in nature. They come from group theory, so that's algebra. Actually, I went through a proof of the Banach-Tarski Theorem in my graduate group theory class very recently. Another point of discussion requires emphasis. The whole time, we're talking about dissections or partitions into a finite number of pieces. If we were to allow partitions into an infinite number of pieces, then the entire paradox or puzzle disappears. Because then, every dimension, this partition, this dissect and reassemble operation becomes trivial, in a sense. Because the sets would then have the same cardinality and the cardinality of the continuum. Two sets with the same cardinality you can dissect into singleton sets and reassemble them to get from one set to the other. For example, in one dimension, here's the picture. Trust me that both the intervals b1 and b2 have exactly the same length as the interval b. There's an optical illusion that makes them look different in length. This picture is intended to convince you that there's a one-to-one correspondence between a unit interval and the union of two unit intervals. So essentially, we can dissect or partition the unit interval and reassemble to two copies of the original interval, except you're using singleton sets for your partition here. And there's one minor detail about this picture that is misleading, which is what happens at endpoints. That's a minor detail that we have actually learned. The distinction between closed and open sets becomes a bit of a snag here, but in the Banach-Tarski theorem, the balls we had were closed, and when we dissected into pieces, we were paying close attention and not overlooking whether a point is a boundary point. We can do the Banach-Tarski proof without having to worry about that.